There is a number that should haunt you, not because it is frightening in the conventional sense. No catastrophe hides behind it, no countdown, no explosion. It haunts because of what it reveals about the very ground beneath every assumption we have ever made about reality. That number is 5%. 5. Out of everything that exists across the entire span of the observable universe, every star that has ever burned, every planet that has ever formed, every ocean, every mountain, every atom in every living thing that has ever drawn breath on any world anywhere, all of it, the totality of the physical reality we have ever touched, seen, measured, or imagined, accounts for just 5% of what is actually out there. The other 95% is something else, something stranger, something that does not glow, does not shine, does not cast shadows, does not absorb a single photon of light at any wavelength from the longest radio wave to the most violent gamma ray in the cosmos. Most of the universe is made of things we have never directly seen, and of that vast silent majority, roughly a third, about 27% of all the energy and mass in existence, is a substance so fundamentally alien to our instruments that every telescope humanity has ever constructed is, with respect to it, completely blind. We call it dark matter, and it built everything you have ever looked at. If this kind of journey into the deep unknown excites you, it would mean a great deal to us if you liked this video and subscribed. It helps us keep exploring these ideas together. The story of how we came to know this, how we stumbled onto the greatest hidden architecture in the cosmos, is not a tidy sequence of eureka moments. It is something messier and more human, decades of ignored measurements, careers built on questions nobody wanted to hear, instruments pushed to their absolute limits, and the slow, relentless accumulation of evidence that could not, eventually, be argued away. It is a story about what it means to know something you cannot see, and it begins, as so many profound discoveries do, not with a grand experiment in a gleaming laboratory, but with a single astronomer staring at numbers that simply refuse to behave. Picture the night sky above a mountain observatory in the early 1930s. The instruments are mechanical, the photographic plates are chemical, and the universe, as far as most scientists are concerned, is well mapped and reasonably well understood. The galaxies have been cataloged, their distances are being measured. The great debate about whether certain fuzzy smudges in the sky are clouds within our own galaxy or entire separate galaxies, island universes separated by unimaginable gulfs of space, had only recently been settled in favor of the grander picture. The cosmos is vast. It is populated by billions of galaxies, and it is, at its heart, orderly. Or so everyone assumed. A Swiss-American astronomer named Fritz Zwicky did not share this assumption. Zwicky was many things simultaneously: brilliant, combative, eccentric, and possessed of an almost reckless willingness to follow evidence wherever it led, regardless of weather. The destination was comfortable. He was studying a dense congregation of galaxies known as the Coma Cluster, a gravitationally bound system of over 1,000 galaxies clustered together like a swarm of fireflies frozen in time. His goal was conceptually simple. He wanted to measure the cluster's mass. The method was straightforward. By clocking how fast the individual galaxies were moving as they orbited the cluster's collective center of gravity, he could use classical mechanics to calculate how much mass was needed to hold the whole system together. More mass means stronger gravity. Stronger gravity means faster orbital speeds. The math was not complicated. What he found shattered the comfortable picture entirely. The galaxies inside the Coma cluster were moving at speeds so extreme that the total visible mass of the cluster, every star in every galaxy that his telescope could detect, could not possibly generate enough gravitational force to keep the system bound. By his calculations, the cluster needed somewhere in the neighborhood of 400 times more mass than was actually visible. Not 40 times, not 4 times, 400. The galaxies should have been flying apart in all directions, scattered across intergalactic space like shrapnel. The fact that they were clearly still together, still orbiting, still gravitationally bound, meant something enormous was present that could not be seen. He gave this invisible component a name borrowed from German, Dunkelmaterie, dark matter. And then the scientific community, busy with other things and deeply skeptical of the abrasive Swiss, largely ignored him for the next 4 decades. The universe kept its secret. The evidence sat in print, cited occasionally by those willing to read past their assumptions, but not taken seriously. Zwicky had been right, but being right at the wrong moment in history is sometimes indistinguishable from being wrong. The instruments of the 1930s were too crude to satisfy skeptics. The idea itself was too strange. And Zwicky's personality had earned him enough enemies that dismissing his work felt, to some, less like intellectual rejection and more like a satisfying act of justice. But the universe does not adjust its behavior to accommodate human politics. The evidence continued to build in the background, quiet and patient, waiting for someone with better instruments, better data, and a more systematic approach to finally look at it without flinching. That someone was Vera Rubin. Rubin was not interested in fighting. She was interested in understanding. Working at the Carnegie Institution in Washington in the late 1960s and through the 1970s, she collaborated with instrument designer Kent Ford to conduct something that might sound, on the surface, mundane, careful measurements of how fast stars at different distances from the centers of spiral galaxies were orbiting. Rotation curves, these measurements were called. A plot of orbital speed on the vertical axis, distance from the galactic center on the horizontal. The expected shape was well understood, derived from the same Newtonian mechanics that governs planetary orbits and has been tested relentlessly for 3 centuries. Objects closer to a central mass move faster. Objects farther away move slower. This is not a subtle effect. It is built into the mathematics of gravity at the most fundamental level. Our own solar system demonstrates it beautifully. Mercury races around the sun at nearly 48 kilometers per second, while Neptune, way out in the cold dark, plods along at barely 5. The farther you go from the source of gravity, the slower you move. This must be true. Except, when Rubin and Ford looked at real galaxies, it wasn't. The stars in the outer regions of spiral galaxies, the dim, sparse edges far beyond the bright central disk, where most of the visible mass was concentrated, were not slowing down. They were moving just as fast as stars much closer to the center. The rotation curves, instead of falling off as expected, remained stubbornly, inexplicably flat. Mile after mile, kiloparsec after kiloparsec out into the dark periphery where no significant luminous matter existed, the stars and gas clouds maintained the same orbital velocity, as if the mass responsible for pulling them along extended invisibly far beyond where any telescope could see it. The implications were staggering and immediate. Either the law of gravity, the law that had been confirmed by centuries of precise observation that guided spacecraft through the solar system with pinpoint accuracy, that described the behavior of binary stars and entire galaxy clusters, was somehow wrong on galactic scales. Or there was an enormous quantity of mass present in those outer regions that was not showing up in any observation. Not a little extra mass, not an overlooked cloud of gas here or a dim star there, an entire vast invisible structure extending far beyond the visible edges of every galaxy, containing more total mass than all the stars and gas clouds that could actually be seen. Rubin did not make a dramatic announcement based on a single measurement. She was systematic. She measured one galaxy, then another, then dozens, then hundreds. Different galaxies, different sizes, different ages, different orientations. Galaxy after galaxy after galaxy showed the same result. The flat rotation curve was not a measurement error. It was not an instrument artifact. It was a universal property of spiral galaxies, as consistent and reliable as the fact that their stars emit light. Every galaxy Rubin examined was embedded in something invisible, a vast halo of mass that extended far beyond the glow of its stars, shaping the motions of everything within it, while itself remaining completely transparent to every observing technique available. When other astronomers turned their own instruments to the problem, the evidence only deepened. Radio telescopes, tracing the 21-centimeter emission line of neutral hydrogen gas, pushed the measurement farther out than optical instruments could reach, into the truly dark regions beyond where any stars existed at all. And still, the rotation curves refused to fall. Whatever was out there in the darkness, pulling on gas clouds at the very periphery of galaxies, extended even farther than Rubin's measurements had implied. The invisible halo was enormous. It dwarfed the visible galaxy at its center the way an ocean dwarfs a boat. By the early 1980s, the astronomical community had moved past skepticism into something resembling reluctant acceptance. The evidence was too consistent, too reproducible, too multi-layered to dismiss. Something was wrong with the cosmic inventory. Galaxies were heavier than they looked, dramatically, fundamentally, irreducibly heavier. And the extra mass, whatever it was, did not interact with light in any detectable way. But rotation curves, however compelling, were still a single line of evidence. They addressed the internal dynamics of individual galaxies. Science demands more than one window onto the truth before accepting something this radical. The demand would be answered, again and again, from directions no one initially expected. The first, truly independent confirmation came from a phenomenon that Einstein himself had described in 1915 when he laid out his general theory of relativity and rewrote the entire conceptual foundation of physics. Newton had described gravity as a force, an invisible tug between masses, acting instantaneously across any distance, obeying a precise inverse square relationship. It worked beautifully for 3 centuries. But Einstein realized it was wrong, not dramatically wrong, not wrong in ways that everyday experience would expose, but wrong in the deepest possible sense, wrong about what gravity actually is. In Einstein's picture, space and time are not separate, static backdrops against which events unfold. They are a single flexible fabric, space-time, and mass and energy warp that fabric the way a heavy object distorts a stretched rubber sheet. What we experience as gravitational attraction is not a force at all. It is the natural tendency of objects to follow the straightest possible paths through curved space-time. The Earth does not fall toward the Sun because the Sun is pulling it. The Earth follows a path through curved space-time, and that path happens to be in orbit. The geometry of space itself is the mechanism. One of the most dramatic predictions that follows from this picture is gravitational lensing. When light from a distant source travels toward us and passes near a massive object, a galaxy, a cluster of galaxies, the space-time around that mass is curved, and the light follows the curvature. Its path bends. From our point of view on Earth, this bending distorts the apparent positions and shapes of background sources. A galaxy directly behind a massive foreground cluster might appear as a ring of light, a perfect Einstein ring, or, more commonly, as a series of arcs and smears as the light is bent around the lensing mass along multiple paths simultaneously. This is not a gentle, subtle effect. Around the most massive clusters, background galaxies are stretched and distorted into spectacular luminous arcs that can be seen in photographs from the Hubble Space Telescope with immediate, dramatic clarity. Here is what makes lensing so powerful as a probe of dark matter. The degree of bending depends on the total mass causing the curvature, not just the visible mass, not just the mass that emits or absorbs light, but every last particle of mass in the lensing object, regardless of whether it is electromagnetically detectable. Space-time curves in response to energy and mass with absolute impartiality. A kilogram of dark matter curves space-time just as much as a kilogram of hydrogen gas. The geometry does not distinguish. So when astronomers carefully measure how much the background galaxies are distorted behind a foreground cluster, they are measuring the cluster's total gravitational mass, the complete inventory, dark and luminous alike. And when they made those measurements, the answer came back the same as always. The total mass required to produce the observed lensing was 4, 5, 6 times larger than the mass visible in the galaxies and hot gas of the cluster. Most of the mass was invisible. It was distributed not as the galaxies were distributed, but in a diffuse, extended halo surrounding the entire cluster. The same invisible structure that rotation curves had revealed around individual galaxies was present around galaxy clusters, and gravitational lensing was mapping it directly. Astronomers developed increasingly sophisticated techniques to exploit this. Strong lensing, where background galaxies are bent into dramatic arcs and multiple images, mapped the densest central regions of clusters. Weak lensing, where the distortion is far more subtle, a slight statistical tendency for background galaxies to appear slightly elongated in coherent patterns, mapped the mass. Distribution over far larger areas, reaching out into the extended halos and even into the vast cosmic filaments connecting clusters across hundreds of millions of light years. By combining these techniques, researchers constructed detailed maps of where mass actually was in the universe. And those maps showed, with the cold clarity of geometry, that mass and light were not the same thing. Most of the mass existed in regions of space where the light was absent or faint. The invisible dominated the visible everywhere the measurements were pushed. But even all of this, the rotation curves, the cluster dynamics, the lensing maps, pale slightly in emotional and scientific impact compared to a single extraordinary cosmic event that took place roughly 150 million years ago, whose aftermath astronomers are still studying today. It is called the bullet cluster, and it is the closest thing we have to a direct photograph of dark matter's existence. Two galaxy clusters, each containing hundreds of galaxies and vast quantities of superheated gas, collided with each other. Not a gentle brushing encounter, but a high-speed collision at roughly 4,500 kilometers per second, about 1.5% of the speed of light. What makes this collision uniquely revelatory is what happened to the different components of each cluster during the impact. The individual galaxies within each cluster behaved predictably. Galaxies are separated from each other by such enormous distances relative to their own sizes that even in a cluster collision, direct galaxy-on-galaxy encounters are extraordinarily rare. The galaxies from both clusters essentially passed through each other like two swarms of bees flying in opposite directions through the same airspace. Most of the bees never collide. They sail through the encounter and continue on their original paths. The hot gas was different. The intracluster gas, a thin but extraordinarily hot plasma heated to tens of millions of degrees, glowing fiercely in X-rays, fills the space between galaxies in a more continuous distribution. When the two clusters met, their gas clouds collided head-on. Gas interacts electromagnetically. The charged particles in the plasma ram into each other, generating pressure, friction, shock waves. The two gas clouds decelerated violently and piled up in the middle of the collision zone, compressed and heated even further, blazing in X-rays like a celestial collision marker. When astronomers pointed the Chandra X-ray Observatory at the aftermath of this collision, they saw exactly this, a dense, brilliant knot of X-ray emitting gas sitting between the two clusters' positions, the remains of the Great Gas Collision. Now here is where it becomes extraordinary. Simultaneously, astronomers used gravitational lensing to map the total mass distribution of the same region. They carefully measured the shapes of thousands of background galaxies, extracted the weak lensing signal, and produced a map of where the gravitational mass was actually concentrated. The mass was not where the gas was. The total mass, the gravitational mass, the mass that curves spacetime, was concentrated in two separate clumps on either side of the glowing X-ray gas, roughly coinciding with where the galaxies themselves had gone after sailing through the collision. The bulk of each cluster's mass had not decelerated with the gas. It had kept moving. It had passed through the collision zone as if the other cluster wasn't there. No friction, no electromagnetic interaction, no pressure, no resistance of any kind. The mass had separated from the ordinary matter. Think carefully about what this means. In any hypothesis where the apparent extra gravity comes not from invisible mass but from some modification of how gravity works, a theory where there is no dark matter, only altered physics, the gravitational influence should follow the visible matter. The gravity is produced by what you can see. It simply works differently than Newton predicted. But in the bullet cluster, the gravity does not follow the visible matter. It is physically located somewhere else. It has separated from the gas, which is where most of the ordinary baryonic mass resides. The only way to make sense of this is to accept that there is real, physical mass present, actual material stuff that does not interact electromagnetically. That passed through the collision without slowing down, because electromagnetic interactions are precisely the mechanism through which ordinary matter experiences pressure and friction. The mass is real. It is just made of something that doesn't talk to light. The bullet cluster was not unique in this regard. As astronomers searched more carefully, they found other merging clusters showing the same separation of visible and total mass. Each one told the same story. The invisible component passes through collisions while ordinary matter gets stuck. The fingerprint is always the same because the physics is always the same. Dark matter does not interact electromagnetically. This is not inferred indirectly. In the bullet cluster, you can see it. The mass and the light are in different places. And yet, all of these observations share one limitation. They tell us where dark matter is and how much of it exists, but they speak to the universe as it is now, or as it was in the relatively recent past. The most profound and ancient testimony comes from a time before any galaxy existed, before any star had ignited, before the universe had cooled enough to allow atoms to form at all. It comes from a faint hiss of microwave radiation that fills the sky in every direction, the leftover light from the universe's fiery infancy, preserved across 14 billion years of cosmic expansion. This is the cosmic microwave background, and it is the oldest photograph in existence, released when the universe was only 380,000 years old, a moment cosmologists call recombination, when the cosmos cooled just enough for electrons to pair with protons and form neutral hydrogen atoms, allowing light to finally travel freely through space. This radiation carries within its subtle temperature variations an extraordinary archive of cosmic history. The fluctuations in this ancient light, temperature differences of only about 1 part in 100,000, are the fossilized imprints of density variations in the primordial universe. Regions that were slightly more compressed were slightly hotter. Regions that were slightly more rarefied were slightly cooler. The pattern of these variations, distributed across the entire sky, encodes the composition and dynamics of the early universe, the way tree rings encode the history of a forest. Before recombination, ordinary matter was locked in a hot, dense plasma alongside photons, a seething mixture where electromagnetic radiation and charged particles were so tightly coupled that they behaved as a single fluid. Gravity tried to pull this fluid into denser concentrations, compressing the slightly overdense regions, but photons pushed back. The radiation pressure of the trapped light resisted compression with enormous force, pushing the fluid outward, causing it to rebound and then compress again, oscillating back and forth in what were, quite literally, sound waves. Ancient, primordial sound waves propagating through the hot plasma of the early universe, acoustic oscillations at the dawn of time. Dark matter was doing something entirely different during this same epoch. Because dark matter does not interact with electromagnetic radiation, it was not coupled to the photon fluid. It did not feel radiation pressure. It did not bounce and oscillate with the ordinary matter and light. It simply responded to gravity, freely, without opposition. While ordinary matter oscillated helplessly in the grip of radiation pressure, dark matter was quietly accumulating in the deepest gravitational wells, growing denser, building up the gravitational potential that would eventually guide all of cosmic structure formation. This difference leaves a precise and measurable signature in the cosmic microwave background. The oscillations of the ordinary matter and photon fluid produce a characteristic sequence of peaks and troughs in what physicists call the power spectrum of the CMB, a mathematical decomposition of the temperature fluctuation pattern into contributions from different angular scales. The relative heights of these peaks encode the ratio of different ingredients in the early universe. More dark matter shifts the peaks in one specific, calculable way. more ordinary matter shifts them in another. The two effects are mathematically distinct. By measuring the peaks with sufficient precision, you can read off the cosmic recipe. Satellites dedicated to this measurement, launched over successive decades with ever-increasing sensitivity and resolution, produced data of astonishing precision. The results were unambiguous. The universe contains roughly 5 times more dark matter than ordinary matter. About 27% of the total energy budget of the universe is dark matter. About 5% is ordinary baryonic matter, the atoms and molecules we know, the material everything visible is made of. The remaining 68% is dark energy, a completely separate and even more baffling phenomenon, but that is a different story for another time. What matters here is that this CMB measurement has nothing to do with rotation curves, nothing to do with gravitational lensing, nothing to do with cluster dynamics or the bullet cluster. It uses completely different physics, acoustic oscillations in a primordial plasma at a different epoch of cosmic history, hundreds of millions of years before the first galaxy existed, and it gives the same answer, the same ratio, 5-to-1, dark matter over ordinary matter, consistent to within measurement uncertainties confirmed by multiple independent satellite missions, each using different detector technologies and analysis methods. The CMB also tells us something about dark matter that goes beyond simple accounting. It reveals that dark matter was not merely a passenger in the early universe, but its primary structural architect. Here is the problem that dark matter solves at the most fundamental level of cosmic history. Without it, the universe we observe today should not exist. The density fluctuations in the CMB, those 1 in 100,000 temperature variations, represent the seeds from which everything was supposed to grow. These seeds were extraordinarily small. For them to grow into the mountains of mass we call galaxies and galaxy clusters, gravity had to work on them for billions of years, pulling more and more matter into the dense regions, amplifying the initial fluctuations into the towering structures of the cosmic web. The calculation is well understood. You start with the initial conditions, you apply gravity, you let time run, and you see what you get. The answer, when you run that calculation without dark matter, is wrong. Profoundly, irreparably wrong. Ordinary matter alone, starting from fluctuations of 1 part in 100,000, starting its free gravitational collapse at recombination, cannot build the galaxies and clusters we observe today within the 13.8 billion years the universe has been expanding. The universe is expanding. As it expands, the density of matter decreases, weakening the gravitational force that drives structure formation. The race between gravity and expansion is close, and without dark matter, gravity loses. The universe should be a thin, essentially featureless mist of hydrogen gas. No galaxies, no stars, no planets, no chemistry, no life. But dark matter was not oscillating with the photons. It was not subject to radiation pressure. From the very beginning, from the first fractions of a second after the Big Bang, when the density fluctuations were first imprinted, dark matter was free to respond to gravity. By the time recombination occurred and ordinary matter was finally liberated from the photon fluid, dark matter had already been collapsing for 380,000 years. It had already built the gravitational wells, deep, invisible basins of potential energy into which ordinary matter immediately began to fall the moment it was free to do so. Dark matter had done the patient, invisible preparatory work. Ordinary matter inherited a universe already structured, already scaffolded, already organized on the largest scales. All it had to do was fall. This is why the large-scale structure of the observable universe, the cosmic web, that breathtaking network of filaments and voids and nodes that represents the largest coherent structure in existence, traces the distribution of dark matter. The filaments we map using the positions of galaxies are the luminous outlines of dark matter concentrations that formed first and defined the architecture of everything. The nodes where filaments intersect, the locations of the greatest galaxy clusters, are where dark matter accumulated most densely. The vast empty voids between filaments, Regions that appear to contain almost nothing when mapped by galaxy surveys are precisely the regions where dark matter was slightly less concentrated, from which all matter, dark and visible alike, drained away toward the denser surroundings over billions of years. Enormous computer simulations, running on the most powerful supercomputers available, modeling billions of particles of dark matter and ordinary matter across cosmic volumes, have tested this picture with extraordinary rigor. Starting from the initial conditions encoded in the CMB, these simulations evolved both components under gravity for 13+ billion years. The results are stunning in their fidelity. The simulated cosmic webs bear a remarkable resemblance to the real one. The filamentary structures, the cluster masses, the void statistics, all reproduced without invoking any physics beyond what is already known, as long as dark matter is included. Without dark matter, the simulations produce a universe that looks nothing like the one we live in. With it, the match is striking. So here we stand, 6 independent channels of evidence, each using different physical principles, different instruments, different epochs of cosmic history, different spatial scales, galaxy rotation curves measured over decades by dozens of independent research groups, galaxy cluster dynamics tracing velocities of individual galaxies within bound systems, gravitational lensing mapping total mass distributions around clusters and along cosmic filaments, the direct spatial separation of visible and gravitational mass in merging cluster systems, the acoustic oscillation pattern in the cosmic microwave background, and the formation history of large-scale structure itself, which cannot proceed as observed without dark matter's head start. All 6 converge on the same answer. There is roughly 5 times more dark matter than ordinary matter. It does not interact with electromagnetic radiation. It is everywhere, and we have never directly touched a single particle of it. This last point deserves careful attention because it is one of the most disorienting facts in all of science. We know dark matter is real. The evidence is overwhelming. We know approximately where it is, distributed in halos around galaxies, in filaments connecting clusters, permeating the space around us right now in quantities that should, by the reckoning of cosmological models, send hundreds of thousands of particles streaming through every square centimeter of Earth's surface every single second. We know how much there is. We know what it does. We can calculate its density in our galactic neighborhood to reasonable precision. And yet, despite decades of searching with instruments of extraordinary sophistication, buried kilometers underground in the most isolated sites on Earth, no experiment has ever confirmed the direct capture of a single dark matter particle. Not one. This is not a small failure. These experiments are engineering achievements of the highest order. The detectors used in the search for dark matter are among the most sensitive instruments human civilization has ever constructed. They are placed in deep underground laboratories, beneath mountains, at the bottom of old mines, inside ancient rock formations that took hundreds of millions of years to form. Because the surface of the Earth is constantly bombarded by cosmic rays, high-energy particles from space that would drown any faint signal and noise. The rock above the detectors, sometimes a kilometer or more of it, acts as a shield, absorbing the cosmic ray background until only the rarest and most penetrating particles can reach the detector. The detectors themselves are built from materials purified to a degree that would have seemed fantastical to chemists a generation ago. Even a single radioactive atom of the wrong element hiding within the crystal structure of the detector material can produce a false signal indistinguishable from what a dark matter-particle collision would look like. Every trace of uranium, thorium, potassium-40, radon, every naturally occurring radioactive isotope must be removed or accounted for. The teams that build these detectors have developed purification techniques that push the limits of what is chemically achievable, and then they cool the entire apparatus to temperatures within a fraction of a degree of absolute zero, because thermal noise at room temperature would completely mask the tiny energy deposited by a colliding dark matter particle. The physical principle behind direct detection is elegant. If dark matter particles are streaming through Earth in the quantities that cosmological models predict, and if they occasionally interact with ordinary matter through any force beyond gravity, even an extraordinarily feeble one, then very rarely a dark matter particle might transfer a tiny amount of momentum to the nucleus of an atom in the detector. The nucleus would recoil, moving just slightly from its position in the crystal lattice. That motion, barely a whisper of kinetic energy, would produce a faint pulse of light or an electrical signal, or a tiny temperature increase, depending on the detector design. Catch enough of these whispers, and you have a confirmed detection. The detectors are built to catch whispers that would be inaudible to any other instrument on Earth. The silence has been complete. The most sensitive xenon-based detectors have accumulated years of data with no confirmed signal. Germanium-based experiments at the deepest underground laboratories have set limits on how strongly dark matter can interact with ordinary matter that are orders of magnitude more stringent than anyone thought possible 2 decades ago. Each new generation of experiment pushes the sensitivity further, constraining the allowed interaction rates to ever smaller values. And each new generation of experiment reports the same result: nothing. This silence is itself information. It tells us that if dark matter does interact with ordinary matter through any force other than gravity, it does so at a rate so vanishingly small that our best instruments, operating for years in the most radiation-shielded environments on Earth, cannot catch it. The original leading theoretical candidate for dark matter, a class of hypothetical particles called WIMPs, or weakly interacting massive particles, was attractive precisely because a calculation rooted in the physics of the early universe suggested that particles with masses and interaction rates in a range that experiments could probe should be produced in the right quantities to account for the observed dark matter density. This coincidence, called the WIMP miracle, drove experimental efforts for decades. WIMPs with the predicted properties should have been found by now. They have not been. The simplest WIMP models are under severe pressure. The parameter space where they were expected to live has been extensively explored, and the search has come back empty. This does not mean dark matter is wrong. The gravitational evidence is immovable. Dark matter exists. What it means is that dark matter is not what the simplest theories predicted, and the true nature of dark matter may be more exotic, more subtle, or simply different in ways that our current theoretical imagination has not fully grasped. The absence of a detection in WIMP searches is a constraint, not a refutation. It says, whatever dark matter is, it is not this particular thing at these particular parameters. The solution space has been narrowed, which is itself progress. Other candidates have attracted increasing interest as the WIMP landscape has thinned. Among the most theoretically compelling is a class of particle called the axion. The axion was not invented to solve the dark matter problem. It was invented to solve a completely different puzzle in particle physics, a puzzle about why the strong nuclear force which governs the interactions of quarks inside protons and neutrons exhibits a particular mathematical symmetry that it has no obvious reason to respect. The strong force, as described by quantum chromodynamics, allows for processes that would violate a symmetry called CP symmetry, the combined symmetry of charge conjugation and spatial reflection. Experiments show that the strong force conserves this symmetry to extraordinary precision. The equations say it shouldn't have to. Something is enforcing the symmetry, and nobody knew what. In 1977, physicists Roberto Peccei and Helen Quinn proposed a solution, a new symmetry that, if broken in a particular way, would automatically drive the strong force toward CP. Conservation. The breaking of this symmetry would inevitably produce a new type of particle, a consequence as inexorable as a ripple produced by a stone thrown in still water. Two physicists, Frank Wilczek and Steven Weinberg, independently worked out the properties of this particle and named it the axion. Axions, if they exist, are extraordinarily light, perhaps 1,000,000 times lighter than an electron, or even less. They interact with ordinary matter so feebly that they make neutrinos look almost gregarious, but their very lightness, paradoxically, can be an asset for dark matter. Light particles produced in the early universe through a mechanism called vacuum misalignment would be created in enormous numbers. Individually nearly massless, collectively they might represent a significant fraction of the total mass energy budget of the universe. A vast, cold sea of nearly invisible, nearly massless particles, too numerous to count, filling the cosmos. Detecting axions requires a completely different approach from WIMP hunting. The key is a process predicted by quantum field theory. In the presence of a strong magnetic field, an axion has a tiny probability of converting into a photon. The probability is minuscule, but if you create the right conditions, a powerful magnetic field, a precisely tuned microwave resonant cavity that amplifies the signal when its resonant frequency matches the photon energy corresponding to a given axion mass, you can scan through possible axion masses and listen for the faint photon signal that would betray their presence. Dedicated axion experiments around the world have been scanning through axion parameter space for years, gradually covering more ground with improving technology. No detection yet, but the search is active and the technology is advancing. There is a third category of candidate worth understanding, not just for its scientific content, but for what it reveals about how wide open the dark matter question still is. Sterile neutrinos are hypothetical relatives of the known neutrino species that lack even the weak force interaction that makes ordinary neutrinos detectable. They would interact only through gravity and through an extremely suppressed quantum mixing with ordinary neutrinos. If they have masses in the right range, they could be produced in the early universe in quantities sufficient to account for dark matter. And if they decay very slowly, on timescales far longer than the current age of the universe, they would occasionally produce a photon at a specific X-ray energy, a faint spectral line that telescopes might detect in the X-ray emission from galaxy clusters where dark matter is densely concentrated. In 2014, observational astronomers examining data from multiple X-ray telescopes reported an unidentified emission line at an energy of roughly 3.5 kiloelectron volts appearing in spectra from several galaxy clusters. The energy was consistent with the decay signature expected from a sterile neutrino of a certain mass. The dark matter community paid close attention. Subsequent observations produced conflicting results. Some telescopes confirmed the line, others did not. Analysis of different data sets led to different conclusions. The scientific community remains divided. The signal is real enough to warrant continued investigation, but ambiguous enough to prevent confident interpretation. It remains one of the most tantalizing, unresolved hints in observational astronomy. Beyond particles, there is one other category of dark matter candidate that has attracted renewed attention in recent years, driven partly by a spectacular observational discovery in 2016 when gravitational wave detectors on Earth heard, for the first time, the collision of two black holes. The event was a landmark moment in physics, but it also reignited discussion about a very old idea that dark matter might not be made of exotic particles at all, but of black holes, tiny ancient black holes formed not from collapsing stars, but from density fluctuations in the first fractions of a second after the Big Bang, when the universe was so hot and so dense that random variations could, in principle, create regions compressed beyond the point of no return, collapsing into gravitational singularities before any atom or molecule existed. These primordial black holes, if they formed in the right mass range and in sufficient numbers, would have gravitational mass without electromagnetic interaction. They would not emit, absorb, or scatter light. They would form halos, follow the same trajectories as any other massive dark matter candidate, produce the same lensing signatures, affect galaxy rotation curves in the same way. They would be dark, in the most literal sense, objects of pure gravity, utterly black. Extensive observational campaigns have constrained this possibility severely. Gravitational microlensing surveys, scanning millions of background stars for the characteristic brief brightening that occurs when a compact, massive object passes in front of 1. Have ruled out primordial black holes in many mass ranges. If primordial black holes in certain mass windows comprised all the dark matter, we would expect to see a detectable rate of microlensing events among the stars of the Magellanic Clouds and other nearby stellar populations. The observed rate is too low to support primordial black holes as the dominant dark matter component over much of the accessible mass range. Some windows remain open, particularly at very low masses and at masses in the range of tens of solar masses, provocatively close to the masses of the black hole mergers, detected by gravitational wave observatories. The question is not settled, and the possibility that at least some fraction of dark matter might be primordial black holes has not been eliminated. The honest answer, the answer that physics currently offers, is that we do not know what dark matter is made of. We know it exists with near absolute certainty. We know its gravitational properties with impressive precision, and we do not know its particle identity. This is an unusual position for science to be in, confident about the macroscopic without certainty about the microscopic. But it is not unprecedented. Scientists were confident the sun was powered by some enormous energy source long before nuclear fusion was understood. They were confident bacteria caused disease before they could see bacteria. The large-scale behavior was clear. The underlying mechanism took longer to reveal itself. To truly understand why dark matter is so difficult to detect, you have to understand what detecting anything actually means at the level of fundamental physics. Every measurement, every observation, every experience of the physical world ultimately comes down to an interaction. To know something is there, something must happen. A particle must hit a detector, emit a photon, create a current, deposit heat, disturb an atom. Without an interaction, there is no detection. Without detection, there is no knowledge. This sounds obvious, but its implications are profound. Physics has precisely characterized 4 fundamental forces through which particles can interact with each other and with detectors. The electromagnetic force is the force of light and electricity. It governs the interactions of charged particles and is responsible for virtually every physical phenomenon we encounter in daily life: chemistry, light, magnetism, the solidity of matter itself. The strong nuclear force binds quarks into protons and neutrons and holds atomic nuclei together against the electromagnetic repulsion between their positive charges. The weak nuclear force mediates radioactive decay and certain particle transformations. And gravity pulls all masses together, shaping orbits and cosmic structures, but almost inconceivably feeble at the scale of individual particles. Every known particle interacts through at least one of these forces in a way that can, in principle, be exploited for detection. The photon is literally the mediator of the electromagnetic force. It is what electromagnetic interactions consist of. The electron carries electric charge and interacts electromagnetically with extraordinary strength. Quarks carry both electric charge and a property called color charge that makes them subject to the strong force. Protons and neutrons are composites of quarks and participate in electromagnetic and strong interactions. Even the neutrino, the most spectral and elusive of the known particles, electrically neutral and immune to the strong force, interacts through the weak nuclear force. And this interaction, though extraordinarily rare, is sufficient. Superheated water in underground tanks, large blocks of gallium, tanks of chlorinated cleaning fluid, enormous arrays of photomultiplier tubes surrounding vast volumes of ultra-pure ice in Antarctica. All of these have been used to catch neutrinos to confirm that these ghostly particles are real and measurable because their weak force. Interaction rate, though minuscule, is not zero. Dark matter appears to lack even this last refuge. If it has any interaction beyond gravity, that interaction is below the threshold of what our most sensitive direct detection experiments can measure after years of operation. For all practical experimental purposes, for all purposes beyond the gravitational, dark matter does not interact. It passes through ordinary matter the way a rumor passes through a crowd, changing nothing, leaving no mark, impossible to hold. This single property, the apparent absence of any electromagnetically relevant coupling, is not just what makes dark matter invisible. It is what makes dark matter structurally different from ordinary matter in ways that cascade through every level of physical organization. The consequences extend from the architecture of the cosmos down to the most intimate level of material existence. Consider what the electromagnetic force actually does for ordinary matter. It is the force of chemistry. Every bond that holds a molecule together, the sharing and exchange of electrons between atoms, is an electromagnetic interaction. The covalent bonds in a water molecule, the ionic bonds in table salt, the metallic bonds that give copper its electrical conductivity, the hydrogen bonds that hold the double helix of DNA together, the van der Waals forces that allow gecko feet to adhere to glass. Every last one is electromagnetic in origin. Without the electromagnetic force, there are no molecules. Without molecules, there is no chemistry. Without chemistry, there is no complexity of any recognizable kind. And beneath chemistry, at the level of atoms themselves, the electromagnetic force is equally foundational. An atom is fundamentally an electromagnetic structure, a positively charged nucleus holding negatively charged electrons in orbit through electromagnetic attraction, with the electrons occupying specific quantum energy levels whose properties are entirely determined by the interplay of electromagnetic forces. The number of electrons in an atom and the way they are arranged in shells and subshells around the nucleus determines every chemical property that distinguishes one element from another. The difference between carbon, the backbone of all known life, and nitrogen or oxygen or iron is purely a matter of electromagnetic configuration. Remove the electromagnetic force and you remove the distinction between elements. All matter becomes structureless mass, every particle equivalent to every other particle, indistinguishable not by composition, but by the absence of any structure to distinguish. Dark matter lives in this electromagnetically silent world. Whatever dark matter particles are, they have no electric charge. They cannot form atoms. They cannot bond into molecules. They cannot undergo chemical reactions. They cannot build the extraordinary hierarchies of structure that ordinary matter constructs when its particles are allowed to interact electromagnetically. Dark matter cannot form a crystal, cannot form a liquid, cannot form a gas in any chemically meaningful sense. It cannot build a star because star formation requires gas cooling, the radiating away of thermal energy through electromagnetic emission, and dark matter cannot radiate. It cannot form a planet because planetary bodies are held together by the electromagnetic bonds between their constituent atoms. A dark matter world, a universe populated entirely by dark matter with no ordinary matter at all, would be a place of utter structural simplicity, diffuse halos of invisible mass, drifting through perpetual darkness pulled by gravity into filaments and nodes, but utterly devoid of complexity, variety, chemistry, or light. No surface on which anything could rest. No medium through which any signal could propagate. No structure at any scale smaller than a galactic halo. Eternal, silent, featureless darkness. This is, in fact, the dominant constituent of the universe in which we actually live. The electromagnetically complex, chemically rich, light-filled reality we inhabit, the one that includes stars and planets and oceans and DNA and consciousness, is a minority phenomenon. A 5% exception, a fragile, luminous film spread across the surface of an overwhelmingly dark universe. But here is the profound irony at the heart of this picture. The very property that makes dark matter structurally simple and electromagnetically invisible is precisely the property that made it cosmologically indispensable. Because dark matter could not radiate energy electromagnetically, it could not cool. Because it could not cool, it could not collapse into the thin, dense disks and compact objects that ordinary matter forms. It spread out into diffuse, extended spherical halos, supported against further gravitational compression by the thermal motions of its constituent particles. Motions that could not be shed, because the only way to shed them is to radiate, and dark matter cannot radiate. This inability to collapse into compactness meant that dark matter spread across enormous volumes of space, creating the extended halos and vast filamentary networks that constitute the large-scale framework of the universe. And because dark matter was not subject to radiation pressure in the early universe, because it was free to respond to gravity from the very beginning without the oscillating photon fluid fighting against it, it built up gravitational structure earlier and more efficiently than ordinary matter could. When the universe was still less than 1,000,000 years old, dark matter was already organizing itself into the seeds of the great structures that would eventually define cosmic geography. By the time ordinary matter was freed from the photon fluid at recombination, the dark matter landscape was already sketched out in broad strokes. Ordinary matter fell into the map that dark matter had already drawn. Without this head start, without the electromagnetically silent, cool, collapsing dark matter building the scaffolding while ordinary matter was oscillating in the plasma, there would be no framework for ordinary matter to fall into. The density fluctuations in the CMB are real, but they are too small, and the universe is expanding too fast for ordinary matter to build galaxy-scale structures on its own in the available time. The math is unambiguous. Without dark matter, the universe would not have galaxies. Without galaxies, there would be no stars. Without stars, no nuclear fusion, no heavy elements, no carbon, no oxygen, no nitrogen, no sulfur, no phosphorus, none of the elements that chemistry requires to build the complex molecules of life. Without those molecules, no life. Without life, no one to wonder about any of this. Dark matter did not just build the universe's scaffolding. Dark matter, through its gravitational generosity, created the conditions without which ordinary matter could never have done any of the extraordinary things it eventually did. The 5% that makes everything visible owes its existence to the 27% that remains invisible. We are a consequence of dark matter, downstream of its ancient labor. This relationship, dark matter as unseen architect, ordinary matter as luminous occupant, is captured beautifully in the structure of galaxies themselves, if you know how to. Read it. A spiral galaxy like our own Milky Way presents a picture of luminous complexity. A thin disk of stars with winding spiral arms, hot blue clusters of young stars scattered along. Those arms, older red and yellow stars populating the disk, a central bulge packed densely with ancient stars, thin streams of gas and dust threading through everything. Occasional clusters of hundreds of thousands of stars orbiting in globular clusters above and below the disk. It is one of the most complex and beautiful structures in the observable universe. But the galaxy we see, the luminous disk, is embedded within a halo of dark matter that dwarfs it in every dimension. The visible disk of the Milky Way spans roughly 100,000 light-years from edge to edge. The dark matter halo that surrounds and permeates it extends perhaps 300,000 light-years from the galactic center, possibly more. The exact extent is difficult to measure precisely because it fades out gradually rather than ending at a sharp boundary. In every direction, above and below the disk, stretching out far beyond the last visible star, the dark matter halo envelops the galaxy in an invisible gravitational cocoon. The total mass of this halo is estimated to be several times greater than the mass of all the visible stars and gas combined. The galaxy you can see is the interior decoration of a vast, invisible gravitational structure that extends far beyond any luminous boundary. This geometry is not accidental. It is a direct consequence of the electromagnetic silence we have been exploring. Ordinary matter collapsed into the disk because it could radiate energy, and cooling allowed it to condense into the thin, flat structure we observe. Dark matter could not cool, could not condense, remained diffuse and spherical. The disk is the cooled component. The halo is the uncooled component. Their very different shapes are written in the physics of electromagnetic radiation. The Milky Way's dark matter halo is not just an abstract astrophysical structure. It is physically present around us right now, wherever we are. The solar system orbits within the disk of the galaxy, which is embedded within the halo. Dark matter particles from the halo stream through the solar system, through Earth, through every building and every living body on the planet, at speeds of hundreds of kilometers per second, the orbital speed of the galaxy's rotation, and the random thermal motions of the halo particles combined. The flux through Earth is continuous and enormous. If the standard models of dark matter distribution are correct, something on the order of 100,000 dark matter particles pass through a space the size of your hand. Every second, not occasionally, every second. They pass through your hand, through the table beneath it, through the floor beneath that, through the rock beneath the floor, through the whole planet, and out the other side, without once disturbing a single atom, leaving no trace, producing no signal, doing nothing detectable beyond curving space-time ever so slightly around their collective mass. They are here. They have always been here. They will be here long after the last star in the universe burns out, after every proton has decayed, and the last black holes have evaporated, and the cosmos has settled into its final thermodynamic stillness. Dark matter does not decay on any timescale relevant to stellar or planetary evolution. It does not react. It does not transform. It simply persists, gravitationally faithful, electromagnetically absent, as it has been since the first fraction of a second after the Big Bang. The frustration of this situation for experimental physicists is difficult to overstate. You have a substance that you know is present in enormous quantities, that you can measure through its gravitational effects with precision and confidence. That passes through your detector continuously at a calculable rate, and yet you cannot catch it. The detector sits there, sensitive to the faintest recoil of a single atomic nucleus, cooled to within fractions of a degree of absolute zero, shielded from the cosmic background by kilometers of rock, purified to a degree that removes essentially every known source of spurious signal. And yet, the detector sees nothing. The particles stream through 100,000 per second through every square centimeter, and not one leaves a mark. This is what it means to have access to only one of the four fundamental forces when you are trying to measure something. Gravity works on dark matter. We can exploit that. But gravity between a single dark matter particle and a single atomic nucleus is so unspeakably feeble, roughly 10 to the 36th power weaker than the electromagnetic force between a proton and an electron, that it cannot be detected on the scale of laboratory instruments. We need the gravity of entire galaxy halos before it becomes measurable, and that measurement, profound and valuable as it is, tells us nothing about what the particles are. It tells us where the mass is and how much of it exists. It does not reveal particle mass, spin, interaction cross-section, or any of the quantum properties we would need to identify dark matter and place it within a theoretical framework. The search continues on every front simultaneously. Direct detection experiments are being built larger and more sensitive with each generation, filling cavities the size of houses with ultrapure liquid xenon or argon, covering the detector's surfaces with photomultiplier arrays sensitive to single photons, waiting with mechanical patience for a signal that may or may not come. Indirect detection experiments scan the sky for the photons or cosmic ray particles that might be produced when dark matter particles annihilate or decay, sifting through the enormous background of known astrophysical sources for excesses that might betray dark matter's hidden interactions. Collider experiments at CERN and elsewhere continue to analyze billions of particle collision events, searching for the missing energy signatures that would indicate dark matter production in high-energy collisions. Axion searches scan through the enormous parameter space of possible axion masses and couplings. Sterile neutrino searches analyze X-ray spectra from galaxy clusters with increasing precision. New theoretical ideas are proposed and tested against existing data regularly. The absence of a detection is itself informative. Every null result narrows the possibilities, rules out hypotheses, and forces theorists to think more carefully about what properties dark matter might have. This process, slow and methodical and sometimes frustrating, is how science actually works. It is not glamorous. There are no sudden flashes of insight that resolve everything at once. There is careful measurement, careful analysis, careful inference, and the gradual, inexorable tightening of the constraints on the unknown. We are now, arguably, at a critical juncture in this long search. The simplest theoretical ideas, the ideas that drove the most ambitious experimental programs, have not been vindicated. The easy answers have been ruled out. What remains is harder, stranger, more demanding of imagination. Perhaps dark matter interacts with ordinary matter through forces we have not yet identified, hypothetical new forces beyond the four we know, forces that are even weaker than the weak force and require detectors of a kind not yet imagined. Perhaps dark matter is not a single particle species, but an entire hidden sector, a parallel universe of particles interacting with each other through forces that are analogous to electromagnetism and the strong force, but operate entirely among dark matter particles, leaving ordinary matter untouched. In such a scenario, dark matter might have its own rich internal dynamics, its own equivalent of atoms and molecules and chemistry, but conducted entirely in the dark, invisible to any instrument sensitive to ordinary matter. Perhaps the dark matter particle is so light that current experiments designed for WIMP-scale masses simply cannot reach it, or so heavy that the flux of dark matter particles per detector area is too sparse to produce a measurable event rate within any realistic experimental timeline. The possibility space is large, and the imagination of theoretical physicists in filling it is inexhaustible. What we can say with confidence, and what 6 independent lines of physical evidence demand we say, is that dark matter is real, that it constitutes roughly a quarter of the universe's total energy content, that it does not interact electromagnetically, and that it built the gravitational framework within which all visible cosmic structure formed. These are not speculative conclusions. They rest on decades of observation using instruments and methods that have been independently verified and cross-checked more thoroughly than almost any other result in the history of astronomy and cosmology. The question of what dark matter is at the particle level, what its mass is, how it interacts beyond gravity, how it was produced in the early universe, whether it is a single species or a complex hidden sector, remains genuinely open. This is not a source of embarrassment. It is an invitation. It is the universe leaving a door ajar, showing us a view that extends beyond the illuminated rooms of the known into the vast dark architecture that supports everything we see. There is a particular kind of awe that comes from contemplating this picture seriously, not the comfortable awe of a beautiful photograph or a poetic description, but the deeper, more unsettling awe of genuine confrontation with the unknown. We live in a universe where the majority of the matter has never been directly detected by any instrument, where the substances that dominate reality are utterly transparent to every form of light, where the architecture of everything we see was built by something we cannot see, where hundreds of thousands of particles of an unknown substance stream through our bodies every second without leaving a mark. And yet we know it is there. We know its distribution. We know its abundance. We know its role in cosmic history. We inferred it with mathematics and measurement, and the patient refusal to accept that the numbers could be wrong when they contradicted each other so consistently for so long. We, creatures made entirely of the electromagnetically active 5%, living on a small rocky planet, orbiting an ordinary star in one galaxy among hundreds of billions, figured out that the universe was mostly made of something we cannot directly touch. We noticed the universe was heavier than it looked. We measured the discrepancy with instruments of increasing precision. We tested it from every angle available to us. We built theories, designed experiments, launched satellites, buried detectors in ancient rock, and pointed the most sensitive instruments in human history at the problem from every direction science could reach. And the conclusion across all of those independent lines of evidence was always the same. Most of the universe is dark. Most of the matter is invisible. The visible is the exception, not the rule. We are the exception, the rare, electromagnetically privileged, chemically complex, carbon-based, light-emitting, light-seeing, light-loving minority in a universe built primarily from something that does not know light exists. That dark matter does not know light exists is not a poetic license. It is a precise description of the physics. There is no interaction. Photons pass through dark matter without deflection. Dark matter moves through photons without response. They coexist in the same spacetime, subject to the same gravity, but electromagnetically, they occupy parallel worlds. A dark matter particle floating in the core of the sun experiences the sun's gravity. It does not experience the sun's light. The billions of photons surging past it every instant might as well not be there. The electromagnetic universe, the universe of light and chemistry and complexity and life, is invisible to dark matter just as dark matter is invisible to us. The blindness is mutual, and yet despite this mutual blindness, despite the absolute electromagnetic silence between dark matter and everything we have ever seen, dark matter left its fingerprints all over the universe that light has revealed, in the rotation speeds of distant stars, in the distorted shapes of galaxies bent around invisible mass, in the temperature patterns of the oldest light in existence, in the vast architecture of filaments connecting galaxy clusters across hundreds of millions of light years, in the separation of mass and visible matter during the great collision of galaxy clusters, in the very fact that any galaxy or star or planet exists at all. These fingerprints are not subtle. They are not ambiguous. They are written clearly in every direction we look, in every wavelength of electromagnetic radiation we have used to study the cosmos, at every scale from individual galaxies to the observable universe as a whole. The dark universe has left traces everywhere in the light universe, the way a sculptor leaves traces in the clay, not present in the final form, but responsible for every contour. This is the relationship between dark matter and everything we have ever seen. Dark matter is the sculptor. Ordinary matter is the clay. The sculptures are stars, galaxies, galaxy clusters, the cosmic web itself, and ultimately, on one small world, orbiting one unremarkable star at the quiet edge of one spiral. Galaxy among hundreds of billions, the improbable emergence of beings capable of asking why the numbers didn't add up and patient enough to find out. The answer they found, that most of the universe is invisible, that the majority of matter has never been directly seen, that the architecture of everything luminous was built by something dark, is one of the most extraordinary conclusions in the history of human understanding. It does not diminish what we can see. It illuminates it, if the word can be used for a discovery about darkness. Every galaxy in the night sky is brighter for being understood as the luminous interior of a much vaster, invisible structure. Every star is more remarkable for being an island of electromagnetic complexity in an ocean of gravitational simplicity. Every atom in every living organism is more extraordinary for being part of the rare 5%, the electromagnetically enabled fraction that got to become complex, that got to cool and collapse and bond and react and grow and eventually look up and wonder. Step back for a moment from the technical details and the experimental numbers and consider what this situation actually feels like from the inside, from the perspective of the physicists and astronomers who have devoted their professional lives to this problem. There is a particular psychological texture to working at the frontier of knowledge in a field where the quarry is known to be real but completely elusive, where every instrument reports silence while the theoretical models say the particles are right there, streaming through the detector in vast numbers every second. It is not the frustration of looking for something that might not exist. Dark matter exists. The evidence is beyond serious doubt. It is the frustration of knowing something is present and being completely unable to touch it, like standing in a room filled with a gas you cannot breathe, smell, taste, or feel, but that you can observe bending light rays passing through the space around you. You know it is there. You simply cannot interact with it on human terms. The people who build dark matter detectors are not naive about this. They understand the physics. They know why dark matter is hard to catch. They design their experiments with a clarity about the odds that requires a particular kind of scientific courage, the courage to invest years of work in an instrument that may, and perhaps will, report nothing. The null result is information, but it is cold comfort when a generation of scientific effort has been poured into a question that remains unanswered. Consider the team at a deep underground laboratory, the kind carved out of ancient rock beneath a mountain range where the overburden of stone absorbs the constant rain of cosmic rays from space. The drive-in takes you through a tunnel that goes on long enough, that you forget which side of the mountain you started from. The air inside is cool and slightly damp, the smell of mineral rock everywhere. The detector itself is housed in a cavern that required excavating thousands of tons of rock, every cubic meter of which had to be monitored for natural radioactivity, because even the rock walls could contaminate the measurement. The detector vessel sits at the center of nested shields and veto systems designed to identify and reject every background event that is not a genuine dark matter interaction. Engineers and physicists work in cleanroom suits not because the detector is fragile in the conventional sense, but because a single particle of radioactive dust settling on the detector surface could mimic a dark matter signal. The calibration runs alone take months. You have to understand the detector's response to every known type of particle that might enter it: electrons, photons, neutrons, so precisely that, when an unknown event appears, you can rule out every known explanation before attributing it to something new. You have to know your instrument so well that you trust it absolutely, because the signal you are looking for, if it exists, will be at the very edge of what the detector can see. A handful of events per year, perhaps fewer, perhaps none. And then the running begins. The detector fills with ultra-pure liquid xenon and the photomultiplier tubes that line its inner surface watch for the faint flashes of scintillation light that would signal a nuclear recoil. The electronics record every event. The scientists watch the data accumulate in near real time, running their analysis code daily, watching the background rate, adjusting their models. Weeks become months. Months become years. The background events are studied, understood, cataloged. Every muon that punches through the rock shield, every neutron produced by cosmic ray spallation in the surrounding cavern walls, every electron recoil from trace radioactive impurities in the xenon itself. The background is mapped and characterized with obsessive thoroughness because it is only against the background that a signal could be recognized. And the signal does not come. The data accumulates. The sensitivity improves. The excluded parameter space grows. Theoretical models that predicted dark matter should have been found by now are quietly revised downward or abandoned. The next generation of detector is designed with 10 times the target mass and proportionally greater sensitivity. The cave is expanded. New purification systems are installed. New analysis techniques are developed. The search moves forward. This is not failure. It is science. The absence of a detection is a real measurement. Every null result is a cut through the dark matter parameter space, a boundary that says dark matter, if it exists, cannot have these properties. The excluded regions narrow the possibilities and focus the theoretical imagination. Understanding what dark matter is not is a necessary step toward understanding what it is. But it requires a temperament that can find meaning in the negative, that can sustain attention and energy through years of careful work whose only immediate product is the knowledge that the answer is somewhere other than here. The physicists who do this work are not pessimists. They are genuinely curious, genuinely convinced that the question is worth answering, genuinely committed to the idea that if dark matter has any interaction with ordinary matter, beyond gravity, the right experiment will find it. This commitment is not blind faith. It is grounded in the logic of physics. Interactions tend to be connected. The electromagnetic force and the weak force, once thought to be completely separate phenomena, turned out to be different aspects of a single unified electroweak force. A unification revealed by the mathematics of quantum field theory and confirmed experimentally in the 1980s. The pattern of physics at successively deeper levels of description is one of unification, of apparent distinctions dissolving into shared structures. It is not obviously unreasonable to hope that dark matter, whose gravitational properties are so well characterized, might eventually be connected to ordinary matter through some interaction beyond gravity that we have not yet measured. The connection might be extraordinarily feeble. It might require detectors we have not yet built, but the history of physics gives some reason to believe that things which seem entirely separate sometimes turn out to be related in unexpected ways. There is also the tantalizing evidence from the cosmos itself, the indirect hints that keep the indirect detection community engaged even through years of ambiguous data, the gamma-ray excess from the galactic center that might be dark matter annihilating in the dense dark matter halo at the Milky Way's core, the unexplained X-ray spectral line from galaxy clusters that might be a sterile neutrino decay signature, the various cosmic ray anomalies, excesses of positrons, unusual antiproton flux ratios that some models can accommodate through dark matter interactions. None of these hints is conclusive. Each has a conventional astrophysical explanation that cannot be ruled out with current data, but they exist. The universe keeps producing small, ambiguous signals in the directions where dark matter signal would be expected, and the scientific community keeps analyzing them with increasing sophistication, trying to extract the true information content from the noise. The history of physics is full of examples where ambiguous hints eventually resolved into confirmed discoveries. The detection of the Higgs boson in 2012 was preceded by years of tantalizing excesses in the data that oscillated in significance as more data accumulated, finally crystallizing into an unambiguous signal at a mass that theory had suggested. The detection of gravitational waves from the first binary black hole merger was preceded by decades of theoretical preparation and instrument development, punctuated by false alarms and ambiguous signals before the definitive moment in September 2015 when LIGO heard the universe for the first time. Great discoveries at the frontier of measurement do not typically arrive with sudden, overwhelming clarity. They emerge slowly, haltingly from the noise, requiring patience and rigor and the willingness to be wrong many times before being right once. The dark matter community has been developing that patience for nearly a century. The capacity to wait, to look carefully, to refine and repeat, and to keep going when the answer is not yet there. There is another dimension to this story that deserves attention, a dimension that rarely appears in the technical literature but that shapes the experience of everyone working. In the field, dark matter forces a confrontation with the limits of human sensory intuition that is more profound than most topics in physics. The relativity of simultaneity, the wave-particle duality of quantum mechanics, the curvature of space-time. These are concepts that stretch intuition, that require mental effort. To grasp, that feels strange because they describe a world outside the range of everyday experience, but they describe things that can, in principle, be directly observed or experienced. A muon's extended lifetime can be measured precisely. A photon's interference pattern can be photographed. The bending of light around the sun can be seen during an eclipse. Dark matter cannot be seen. It cannot be photographed. It cannot be directly experienced in any way available to human senses or to any instrument that exists today. Its reality is inferred brilliantly, inferred conclusively, inferred with a level of confidence that exceeds the evidence for many things we take for granted, but inferred. We have never, in any conventional experimental sense, held it in our hands. This places dark matter in a peculiar epistemological position. We are more confident about its existence and its properties than we are about many things we can directly observe, precisely because the evidence for it comes from so many independent directions simultaneously. But the nature of that evidence, gravitational, indirect, emergent from the behavior of things we can see rather than from dark matter itself, keeps dark matter at one remove from the directly tangible. This is not a weakness of the dark matter hypothesis. It is a reflection of what dark matter is. The evidence is as solid as the evidence for the existence of the neutrino before it was first directly detected, or the evidence for the existence of atoms before individual atoms could be imaged. Science has always been capable of reaching beyond direct observation when the indirect evidence is sufficiently convergent and consistent. Dark matter is among the most thoroughly supported inferences in the history of science, but it does ask something of human imagination. It asks us to accept that the universe is not built primarily of the kinds of things we can interact with, that the dominant form of matter is one that exists entirely outside the electromagnetic framework through which we perceive everything. It asks us to extend our conception of physical reality to include something that is gravitationally present but electromagnetically absent, present in the fabric of space-time, but absent from the fabric of light. It asks us to understand that visibility and existence are not the same thing, that the invisible can be real and foundational and overwhelming in its abundance. These are not easy adjustments for minds that evolved to navigate an entirely electromagnetic world, a world where seeing and touching and knowing are so deeply intertwined that we often treat them as synonymous. We trust our eyes almost reflexively. We trust instruments that extend our eyes into ranges we cannot see directly. The shift required to genuinely accept dark matter is a shift from trusting what we can see or instrument to trusting what we can infer from how the things we can see behave. It is a shift that the history of physics has repeatedly demanded, and that the history of physics has shown to be richly rewarded. The scientists who made the key discoveries in dark matter's story, the patient accumulation of evidence from galactic rotation, from cluster dynamics, from gravitational lensing, from the microwave background, were not working in an obvious tradition. They were looking at discrepancies, at numbers that didn't match, at anomalies that didn't fit the expected picture, and instead of explaining them away, they took them seriously. Vera Rubin did not set out to discover dark matter. She set out to measure rotation curves. The flat curves she found were not the answer she was looking for. They were a problem, an anomaly, a result that contradicted the expected behavior of gravitational systems. She followed the anomaly rather than explaining it away, and in doing so, she opened a door that has not been closed since. Fritz Zwicky, 4 decades earlier, did the same. He measured galaxy velocities in the Coma cluster, did the straightforward gravitational calculation, got a number that was absurdly wrong by conventional assumptions, and reported what he found. He was ignored, partly because his personality made it easy to dismiss him, and partly because the idea was genuinely too strange for most people to accept. But the measurement was right. The anomaly was real. The universe was not behaving as expected, and the most honest response to that situation, the scientifically correct response, was to take the anomaly at face value and ask what it meant. The history of science is largely a history of people following anomalies. Every major revolution in physical understanding began with something that didn't fit, Mercury's anomalous orbital precession that Newtonian mechanics couldn't explain, and that general relativity resolved, the ultraviolet catastrophe in classical radiation theory that quantum mechanics emerged to address, the constant speed of light regardless of reference frame that special relativity reconciled. Dark matter is a modern anomaly of the same type, a persistent, multiply-confirmed discrepancy between the visible universe and the gravitational universe that demands explanation in terms of something new. The explanation on offer, dark matter, a new form of matter interacting gravitationally but not electromagnetically, comprising 27% of the universe's total energy content, is not complicated in its basic conception. It does not require exotic mathematics or departures from well-tested physical principles. It requires only the existence of a substance that has never been directly detected, which is a requirement it shares with many historically successful scientific hypotheses. The evidence for it is overwhelming. The identity of the substance remains unknown. This combination, overwhelming evidence for existence, unknown microscopic identity, is precisely the situation that calls for more experiments, more theoretical creativity, and more patience. The next generation of experiments is already in planning and in various stages of construction. Underground xenon detectors with active masses of tens of tons, compared to the few tons of the current leading experiments, are in development with sensitivities that will explore interaction cross-sections many orders of magnitude below current limits. New axion experiments using novel resonator designs and quantum sensing technologies borrowed from quantum computing are being built, capable of scanning axion parameter space far more rapidly than previous instruments. The next generation of CMB observatories will map the temperature and polarization patterns of the microwave background with unprecedented precision, extracting tighter, constraints on the fundamental properties of dark matter from the acoustic oscillation patterns in that ancient light. Wide-field gravitational lensing surveys covering billions of galaxies will map the dark matter distribution of the cosmic web with a fidelity that previous surveys could not approach. And CERN's program of future collider experiments will probe particle interactions at higher energies and with better sensitivity to missing energy signatures than any previous machine. The search is not slowing down. It is accelerating on every front simultaneously, driven by the combination of theoretical urgency and technological progress that has always characterized physics at its most productive moments. The search for dark matter continues. New detectors are being designed and built. New theoretical frameworks are being developed. New observational programs are mapping the cosmic web with increasing precision and reaching deeper into the parameter space of possible dark matter properties. The question of what dark matter actually is, what particle or object carries all that gravitational mass in electromagnetic silence, remains unanswered. It may be answered in the next decade. It may take a century. It may require physics we have not yet imagined, instruments we have not yet conceived, or ideas that have not yet occurred to anyone. And if and when that answer comes, it will not merely tell us what dark matter is made of. It will complete a picture that has been 95% blank for the entire history of astronomy. It will reveal what the universe is actually made of at the fundamental level, not just the luminous, electromagnetically active 5% that we can image and study and measure directly, but the full inventory, the whole reality, the complete accounting of what exists. That is not a minor addition to human knowledge. It is perhaps the deepest single question that physics has ever faced. What is the universe made of? We have a partial answer. The rest of the answer is in the dark. But whatever the answer turns out to be, it will be about something real. Something that is right here, streaming through the room as you read this, threading through the walls and the floor and everything beneath it, present in quantities so enormous. They stagger the imagination, invisible to every instrument we have ever built, yet unmistakably, undeniably, indelibly present in the fabric of everything we see. The silent architect, the invisible majority, the gravitational backbone of a cosmos that would not exist without it. Gravity cannot be silenced. Even when light fails, gravity speaks. And for nearly a century, if you knew how to listen, if you watched the rotation of galaxies, measured the bending of space-time, read the temperature patterns in ancient light, the message was always the same. The universe is heavier than it looks. Most of its mass is invisible, and that invisible mass, silent and unseen since the first moments of cosmic time, built everything you have ever seen in the sky. We are the 5%, and we know beyond any reasonable scientific doubt that we are floating in something vast and dark and foundational that we have never directly touched. Something that shaped us without ever acknowledging our existence. Something that gave us a universe to live in and then quietly, completely withdrew from view. It is out there now. It was out there before the first star ignited, and it will be out there after the last star grows cold. Patient, invisible, and everywhere. The dark matter that built the world, silently passing through it still.